Thank you for the introduction, Jason. I'm very excited to be here. And actually, this is the first time I'm giving a talk to people outside computer science or computer graphics. And hopefully, you'll enjoy the thing I'm talking about. So first, just a very brief introduction about myself. My research interests are mainly focused on computer graphics. That is basically about generating movies or videos with some special effects, especially some visual effects for physical phenomena like this piece of cheese we have seen every day. We want to recreate this kind of physical process in a virtual environment. And my interest is also in 3D printing. So why these two things are connected? 3D printing is about creating real objects, and my research is to build numerical algorithms to model and predict what will happen on these different very complicated structures, and to help to optimize and automated design of these 3D printable objects. So these two areas is connected by numerical simulation, and that is where I feel most excited about. So we want to build computational systems to virtualize, to simulate, to optimize, and to predict different properties and behavior of these systems. So before I get into the real math and the physics, let's just look at some phenomena in our real world. So the first thing is bubbles. So, so when we blow bubbles, we see these very thin films evolve with the blowing wind and change their shape and split into oscillating spheres. And how does this happen? And this is another example about fluid, about surface tension driven fluid. So we drop a rock into a multi-layer of paint. It's not found. Sorry, but well, this is just the picture. The splash forms very beautiful shapes and exhibit very complicated dynamics. And if you notice this boundary, you will find that like this fluid is actually twisting itself, like it's rotating, like not like fluid, but like some kind of rod or cloth. And why does that happen? And the third example is that octopus is a solid. Octopus can deliver very complex motions by deforming itself. And human scientists, like this is research done by Robert Wood's group at Harvard. So they want to create artificial software robots, and they call it Octobot, which can behave like a real robot. And by embedding like different types of structures inside a soft body and 3D print them. And how do we predict the motion of these soft body? And how do we use our computation to optimize it? And the last question, last phenomenon I want to show is something called auxetic material. So an auxetic material is some material that exhibits negative Poisson's ratio. So what does so this thing actually doesn't exist in the real world. What does negative Poisson ratio mean? It means if you stretch some object, some material, and on the other side, or on the other two sides of the stretching, it will not shrink itself as a rubber, but actually it will expand. Or if you squeezing the object in some direction, and the other two directions will also shrink. So this is kind of negative deformation, and it's called negative Poisson ratio. And actually, human scientists can design these types of structures by specifying some local geometry patterns. Like here, this is a conceptual design of one type of auxetic material. And if we repeat this pattern by many times and make it to formulate a new type of material. We usually call it metamaterial in material science. And this kind of material can exhibit some auxetic property or some very extreme auxetic property that doesn't exist in our nature world. So my goal is to use computer to investigate and to automatically design these different types of physical systems. So they range from fluids to solids. And the bridge connecting them is computation. And basically, I want to build geometric data structures, numerical partial differential equation solvers, and multi-scale and data-driven approaches to create simulation and exploration approaches to study these physical systems. This is the first example I want to talk about. It's about super resolution structure optimization. This is our latest work published in our computer graphics conference last year. And so first I want to give some background. So it's about 3D printing. So we are studying the mechanical or material property of some elastic material. So basically, elasticity means it's like it can deform itself. Some object can deform itself like a spring. And you can think of these equations of a three-dimensional spring. Like if you have if this object is very stiff, which means it's hard to deform. It's very soft, so with very low stiffness, and it's very easy to deform. And its motion is described by a set of elastic equations. Like the first one is the equilibrium equation, and second one is the relation between the deformation and the force. It's like Ku equals F in our high school physics. It's called Hooke's law, right? And the third equation, it relates the extra deformation, U is deformation, to the strain or stress. It's a tensor. Well, I think you guys should be very familiar with tensors, and these are tensors to describe the physical motion of these objects. And our goal is to solve this kind of equation, of course. And the first step is to discretize the computation. Right? We want to have a grid. If it's in three-dimensional space, it's a 3D array of voxels, right? And for each voxel, we can actually specify the material. Like if we want to 3D print something, we want to know at this point whether we want to put some material or not put some material. So that is the basic setting of our problem. And our optimization goal is to minimize, like given a certain amount of material, we want to optimize some certain property of this structure or this object. For example, we want to minimize the compliance or maximize the stiffness of this structure. So that is a very interesting problem. For example, if we have a rectangle in 2D, and we want to create something that can bridge these two sides. Like if we have a force applied in the middle, on the middle top, it has to be very stiff. Like it should not crash or it should not deform drastically. So even, for example, 20% of material in this space. So how do we design this structure? Maybe we can design something like this, like this, like this. So what is the optimal? Actually, computer can, well, it's very hard to find the global optimal. That's the first thing I want to say, but you can find many reasonable and interesting local minimums by using our computer program. So that is something called topology optimization. We want to optimize material layout in a given domain for a given set of boundary conditions, like the two points are fixed and the point has a force, and to maximize the system's performance, for example, the compliance. And this is actually an optimization problem with two constraints, right? The first constraint is the physical constraint, describes the elasticity of Ku equals F. And the second constraint is volume constraint. We cannot have volume more than 20% occupying this space. So if we solve this problem, we design some mathematical formula and some heuristic iterative optimizer to solve this problem, we can get some nice structures. And these structures are very easily to be verified by additive manufacturing, like 3D printing. And what's the problem for this? The main bottleneck of this kind of application is its resolution. So basically, if it's an iterative solver, iterative optimizer, we just have 2 steps. Things we discretize our material on a voxelized data on a 3D grid. We basically update our density and then solve the physics according to the updated density. And they update the density again and solve the physics again. And the main bottleneck for this kind of loop is, of course, the FEM solve, right? It's like if we have millions of voxels or 10 millions, 100 millions, like this solver, the scalability of this solver is crucial to the actual resolution we can get for our final design. And that is the challenge lying in between the fabrication hardware and the computational software. And this is actually not very intuitive, because that's not the case for most of the other areas. So in 3D printing or in computational fabrication, the resolution of hardware is way ahead of the resolution of software. And for 3D printer, we can actually print objects on an extremely high resolution. For example, the current 3D printer can have the printing precision of 600 dpi. That means within a centimeter cube, it has millions of voxels. Like you can specify 1 million of material points to define your object, to define your material. But for computational software, like for standard, the state-of-the-art FEM solver, can only handle up to millions of voxels on a workstation. And it is also very difficult to handle heterogeneous structures. Like if we have different materials in this space, it's hard to solve, especially if these materials are with drastically different material properties. So then we need to come up with a solution to boost the resolution, right? So that this is our research. Basically, let's look at the discretization. Like if we have a voxelized space, how do we represent this kind of structure, which is not aligned to a grid, the grid lines or grid voxels? Basically, we just simply voxelize it. Right? We see which voxels is occupied by structure, which is not. And if we increase the resolution, of course, this voxelized structure would be more precise. And so that is what we did what people did in topology optimization. If we can have a high resolution grid, then we can have a better representation of our geometry. So people can do it on GPU and do it on high performance clusters with like tens of millions or even billions of voxels, depending on the computational capability of the machine. And actually, what we did is we want to achieve this kind of resolution on a single workstation that can be afforded by these chips. These chips. I will show some video for this shape just in 2 slides. These are actually bird beaks. We are studying the interior structure of a bird beak by optimizing some simple physical. Actually, that's our highlighted example for this approach. So our goal is to optimize some very complicated structure, which really looks like 3D scan or CT image, but that is actually generated by a computer instead of taking real pictures. And we want to generate these extremely high resolution objects, automated design objects on a single workstation with 50 cores and 2 GPUs that within the budget of $25K. So that is our goal. And from the perspective of computation, like if we want to generate this bird pic, if we want to run topology optimization to simulate this, to optimize this thing, we actually need to handle, if we make it a full resolution grid, we need to handle this number of background voxels. It's around 3 TB memory. And the active voxels actually is much smaller than the total number of background voxels, right? Because this structure is very sparse, actually. Like you see, the black regions are just occupy a small amount of space in this computation. So before I introduce our approach, let me just show you the result for this bird pic. So basically, what we are doing here is we want to use computation to study how could a natural structure like a bird pic can evolve by following some simple physical rules. So here the physical rule is, so we just set it as a very standard topology optimization problem. Like we fix the boundary, for example, and we apply force from the top and the bottom, from left and right here, and we give it some volumetric constraint, like we just want 10% or 20% of the volume is material. What should the interior structure look like if we want to optimize, we want to minimize the compliance of this pic? So this is the structure we get from computation after a few hours or days of computation on workstation. And this is the different views. And actually you can see it looks very much similar to a real bird. I think I showed that picture a few slides ago, but it's actually very, so first it's very much like a hierarchy structure. It's very sparse. It's like a tree or a web structure that is supporting the entire space, but with very thin and very complicated geometries. So that is how the nature evolved the real structure. And if we can have some computational tool to get this resolution, we can actually reproduce the nature structure by just formulating some very simple optimization problem. So the resolution here is the key. So how do we? The compliance. Basically the stiffness of this structure. We just want this thing to be as stiff as possible if only 20% of this volume is occupied by material. Sorry. Image compression problem. Yeah, I'm not very familiar with that area, but maybe, yeah. So I want to present a few key ideas for how to achieve like 1 billion voxel computation on a single workstation. So our basic idea is to take advantage of our modern computer architecture. So the first thing is we want to map from our real physical, three-dimensional physical space to a virtual space in our computer, in our operating system, or on our computer architecture. So basically, we want to reuse some concept from computer architecture, which is called TLB table, page table. So basically, it means a computer actually doesn't have very huge amount of memory, but actually it can specify the address for the memory, which is way beyond its actual physical capacity. That is by some mapping from virtual memory to physical memory by using some translation table called translation look-side buffer, TLB table. So if we can reuse this kind of concept in computer architecture, and we can allocate a number of pages, and for each page it's a small grid, and it's actually corresponding to a small volume occupying this three-dimensional space, and we can map this kind of small volume to a real physical memory basically without any additional cost. We actually don't need to create some other data structure like a hash table or like a tree or anything that needs to accelerate the computation. But actually, we just need to reuse this operating system level tool that can help us to manage our space allocation for our topology optimization problem. And basically, like we can, in our virtual space, in our virtual memory, if we can specify like these structure of volume, can actually compactly mapped to a physical memory by using this TLB table. So that is the idea number one. And also we can establish a mapping from like this grid to a hierarchical high resolution grid. And we are only interested in solving the structures or solving the stiffness around the material we are optimizing for. So we don't really care about the large bulk of volume that is far away from the material and that is not occupied by material. And we can dynamically allocate our computation by looking up this TLB table and by looking at where the materials are in each evolution iteration. So that means we have created a hierarchical sparse populated grid, and we can use this grid to optimize different types of structures that exist in a very large physical space, but actually exhibiting sparse and hierarchical geometric structures. So this is another example, a bridge example. Basically, we fix the two sides and we apply a force on the bottom, and we want to optimize the bridge structure that can hold this load by specifying the boundary condition. And this is some bridge structure that we have never seen on the current state-of-the-art topology optimization using the current topology optimization tools before entering to the resolution of billions of computational voxels. Actually, we are creating some microscope that can help us to observe new kind of structure, discover new kind of structure by still following the same rule, but just boosting the resolution and the computation capability of handling these geometries. And actually, if you zoom in, you can find like this structure is very, very hierarchical, and it's like a tree actually. And within this very zoomed in view, we can still observe different levels of details because our computation grid is able to handle the resolution at this level. And actually, this video is showing us like how sparse this structure is and how we create, how we reduce the computation and cost from the like large bulk of void regions that is unimportant for our optimization. And here is some comparison, like the convergence rate, thanks to this algorithm, to this iterative algorithm in topology optimization. The convergence rate actually is not affected at all by the resolution. Like if we enhance the resolution to 8 times bigger, it still converge within like 60 iterations. Like by solving 60 FEM FEM solves, we can get to some structure regardless of its resolution. And but actually for each FEM solve, by using our sparse and sparsely populated grid, we can actually reduce the computation cost significantly by more than 50%. Sorry? It's, well, the measurement is by compliance. So this, if you get to high-res design, its compliance is a few percent lower than the standard one. It's not significant, but it's still better than a standard design. If we can afford more complicated geometry, we'll get a better performance bridge. And we actually did this comparison. Like we upsample the low-res optimized bridge to the high resolution, and we compare the compliance of these two objects. And the third idea is we need a multi-grid solver. We need a fast solver for our finite element simulation. So basically, we also design some efficient matrix-free linear system solver to solve this finite element method on a CPU workstation. And I'm not going into the details of this multi-grid thing, but the basic ideas is we just create a hierarchy of grid, like with different resolutions. And on each resolution, we try to eliminate the residual, the error in this system. And then we pass the remaining error to the next level, and then eliminate the error on some different frequencies. And by doing this from top and down, and then from down and top, and eventually we can efficiently remove the errors on all frequencies. And if we repeat this process for a few times, or if we use this process as a preconditioner for our conjugate gradient solver, we can actually make this conjugate gradient solver to converge to its right solution within constant number of iterations. So that's the basic idea of multi-grid. And our contribution here is we want to make these matrix operations, like on each level, when you are smoothing the error, you're actually doing a lot of matrix vector multiplication operations. And we made these operations to be extremely efficient on our current computer architecture. Basically, we don't need to create a matrix. We don't need to explicitly store the elements for a sparse matrix every time when we do this multiplication, but actually we do everything on a matrix-free way, which means we don't store the matrix, but we know what is the result for the matrix vector multiplication. And without storing its elements, but we know since it's on a grid, we know its structure, and we also know that we can compute the coefficients for each element on the fly during the computation. And this is actually much faster than we explicitly store a matrix. So basically, I just want to take away message that is, if you visit, well, from the perspective of high performance computing or with architecture, if you visit memory to read something, it is usually 100 times slower than you do a simple operation, a simple multiplication or addition operation. It's 100 times slower. So we should try to not storing things on memory, but instead do the computation as much as you can, if this is a memory-bound problem. And we also take advantage of our modern computer architecture, which is with the concept of pipeline or streamline. Basically, it means the modern is 16 core, and this is not some parallelization, but actually streamline. Like for a single operation, it can actually do a number of the similar operations at the same time when these instructions are in the pipeline. Like if we are doing some vector, for example, vector matrix multiplication or vector addition, we can actually take like 16 numbers or 8 numbers at the same time and do it just within one CPU block or a few CPU blocks. And if we can make our code to be friendly to this kind of operation, then our program will be automatically like 10 times faster, even without you do any kind of threading or MPI or parallelization or GPU. We just try to make this thing to be vector, something called vectorized, to be friendly to our vectorized, the modern vectorized machine. Then we can get a very significant efficiency improvement. So here, let me just, oh yeah, that is the, right. This is the real bird big, and let me just show this.
Complex features and high
Show this structure again,
example,
and you can actually compare the
is optimized on a single
artificial structure and the real
on a background grid of nearly 4 billion voxels.
This is a ray traced view, and also it cuts the cross area to show its interior. And we can do the same thing to design different types of structures. For example, we can apply the same physics to design an airplane wing. Basically, we want these structures to grow inside the geometry of airplane wing, but still try to minimize the compliance and see what the optimized structure should look like. And since our grid is not bounded by any boundary, like it's a TLB table, so we can let our structure to grow from the from a void region, and eventually to design something that is not constrained by a design domain. So we can design any kind of shape or structure that can occupy some space that you don't know ahead of time. And this is another example I want to show. It's a codimensional thin shell structure. So that's a very interesting problem. So we start from a thin shell, and we want to optimize this compliance. Like we add a force on the top, and we fix the bottom, or we add a torsion force on the top, and we just want to see what kind of structure it will get. So what is the best performance structure? Is it a shell, or is it a network of elements, or is it's a combination of two? So this is also an interesting mathematical problem. And the latest discovery by people in the area of topology optimization was actually the best performance structure is simply just a shell. If you make this shell to be thinner, then it should have better compliance than any kind of web-like structure, any kind of filament structure. And our discovery is, well, still slightly different from theirs. Maybe our resolution is not high enough yet to get a completely thin shell, but actually we discovered our computation result is to get some codimensional structure. Like it's a combination of both thin shell and the filament. Like the evolution will lead us to some complicated geometry combining codimension 1 and 2, and eventually to formulate some structure that is within the thin shell, but its occupied region is kind of codimensional. And this is we also did some comparison to show the computational efficiency by activating different types of blocks. Yeah, so that is the first story I want to tell today. It's about how to use computer workstation to build super resolution computation optimization, discover some natural geometries and structures. So the second thing, this is also about topology optimization, but I also want to go to some different direction of multi-scale topology or multi-scale simulation and optimization. So this is something I did at MIT over the last 3 years. So we basically want to study how a local geometry will affect the global behavior of material. So this thing is also very can be seen widely in our nature world. For example, we have the local structure of shark skin. Like this kind of structure will have a better hydrodynamic performance of the shark. We also have this local structure of bone and the microstructure of different 3D printed objects. And our goal is to let the computer to automatically discover and synthesize these different types of microstructures to achieve some high-level functions and designs. So the cornerstone of our computation, of our research is something called microstructure, this cube. And this cube is composed of 2 materials. Like the yellow and blue, you can think of one of them is very stiff and the other is very soft. And if you combine this very stiff material and very soft material together in a cube, and if you repeat this cube for multiple times, for a large number of times, then you will get some material that exhibit properties very different from either of these materials. It could be in between, or it could be outside the range of these 2 materials. So how do we compute this? So there are some computation techniques called homogenization. So basically, we set some periodical boundary conditions, and because it's repeated over space, and we still solve a standard finite element method, and we can actually measure the homogenized material property of this microstructure of this small cube by computation. That is like mapping from a geometric design from a maybe 64 cubed design to a single point in our material property space. Like this microstructure should have the Young's modulus of some number, the Poisson ratio, and shared modulus of some other number. It's a point in that space. And our goal is to use the computation to explore the boundary of this material property space by traversing the possibilities of the combination of these base materials. Like I have two or three materials. What is the maximum or what is the minimum Poisson ratio or Young's modulus it can achieve? It can be 3D printed. So basically we do some data sampling strategies by randomly or by intuitively generate different types of microstructures, and we get some data, we get some point cloud in this space. And our goal is to explore this point cloud, to get to the extreme boundary of this point cloud. The computation strategy is we define this point cloud as an implicit surface, as a level set function in this low-dimensional space. And we want to evolve this level set in its normal direction, it's like in curvature flow, right? And so essentially to sample some point that is outside this level set. So there are a few strategies. First, mental Carlo, random sampling. Like we switch the voxels in this microstructure a little bit and see what, well, if we are lucky, then we may get some point that is outside. Then we can enlarge our level set function. Or we can do some gradient descent optimization. Basically, we know this normal direction of the level set, so we just want to optimize the property of this microstructure towards this direction. And we can also get some point if this optimization can converge outside the level set. So by alternatively doing these two strategies, we can eventually get some boundary which we believe could be the boundary of our 3D printing or of our fabrication achievable microstructure properties. And these properties can be used to formulate another type of topology optimization, which we call full-scale topology optimization. So now the building block, each voxel or grid, is not a single material anymore, but it is actually a microstructure we have 3D printed. So still the mathematical formula is pretty much similar to the one I just showed for the standard optimization. We basically still want to minimize the compliance or the deformation of the structure by satisfying a physical constraint, which is FEM, and a volume constraint. But here, volume constraint is actually a high-dimensional level set constraint. So it means every point should be within the constraint, within our pre-computed boundary. If it's outside, then we cannot fabricate, right? So we should guarantee each point is printable, is fabricable. So that is our new problem. Basically, we use this level set to come up with a new nonlinear optimization problem. Like here is the example. So basically, we can specify some design goal. Like if we want to design a soft gripper, and the design goal could be like on the left, we push this material, push this structure, and we want it its head to grip, to deliver some gripping motion by touching each other. That's our design goal and design space. The base material are these two, and we use this base material to pre-compute a material boundary, a level set function, and use this level set function to constrain our continuous optimization problem. Everything, actually, eventually this is a discrete representation, right? Every voxel is specified by certain number of printing voxels, but in the computation, everything needs to be continuous to guarantee a efficient convergence. So therefore, we actually are optimizing the material properties for each microstructure within this level set. And eventually, after this optimization converges, we map it back to 3D printable microstructures. That is like on this level set function, we have some points that are lying on the boundary, and we want to map them to the real sampled points. And actually, we know their property. There's some gap in between these two designs, but we verify the design, and we both on computation and on real experiment that this gap is acceptable for our computation and engineering problems. And eventually, we can come up with some complicated design like this. And for each voxel, it is actually occupied by, for example, 32 cubed or 64 cubed printing voxels. That is a microstructure. And we validate our approach by running simulations and by running mechanical evaluations on different designs and materials. And we think the error is kind of acceptable for this kind of problem. And we also gave some real fabrications. And here are some examples. Like we can design different type of material that can deliver different type of deformations by giving simple boundary conditions. And this is another conceptual example. We haven't fabricated, we haven't succeeded in real experiment yet, but the idea is we want to control some complicated motion, complicated soft body locomotion by very few number of degree of freedom, a very few number of inputs. For example, here, we want to design a soft ray. We want to encode its motion, encode its flapping wing motion within its material by programming the voxels of its material. And this motion should be controlled by only 2 degrees of freedom, like the contract and the expand of two points along this spine direction. And this is our optimization. We use the same, show this again. We use the same computational two-scale topology optimization framework. And then we can achieve these two modes. And when we alternatively shrink and expand these two holes, we can actually deliver the motion of flapping wing by its material distribution. But this thing is still on computation. So we are figuring, actually the reason why we cannot get to the real, to fabricate a real software robot is actually this model should be nonlinear, but our topology optimization algorithms, like all the examples I have shown you now, are based on linear model. So the computation is simpler, but actually it's less predictive on the region of large deformation. So that is well, I think due to the time limit, I may introduce you the last example, that is Auxetic Material. So basically, so these structures are all designed by human previously. And our goal is to also let the computer to do this, to automatically discover this mechanism that can deliver auxetic or negative Poisson ratio properties. So our assumption or our discovery was, when we created the boundary, the point set for our previous project, we actually found that this point set is big enough to cover most of the human designed auxetic structures. Like every paper in material science, that they propose some analytical formula for a structure. If we sample this structure by discretizing its property, geometric parameters, it's actually corresponding to a low-dimensional curve within this space. And this curve is within our bounding shape. So that's our assumption of the discovery of this work. And we want to figure out, then can we extract more useful information from this point cloud? Can we discover some other structures by analyzing this data? So the answer is yes. So we design some automated material discovery pipeline by combining simulation and this point cloud data. So basically, the idea is we just first look at this region with the negative Poisson ratio. We have sampled a lot of negative Poisson ratio structures, and we do some very standard data analysis or some clustering technique to map these things based on its purely based on its geometric features to some low-dimensional embedding space. And in this space, we further extract the information from O'Leary representation that is on voxels to a Lagrangian representation based on graphs or based on connectivities and particles. Like then we can template-rice each family of microstructure by way fewer number of parameters. For example, here is 6 and convert from a 64 cubed voxel space to maybe a 20-dimensional parameter space. And eventually, then we can do some linear interpolation within this family of microstructures by tuning these parameters, and we will discover how these parameters will affect both the shape and its material property, that is auxetic negative Poisson ratio. So this will just go briefly on this pipeline, and this pipeline can eventually lead us to discover some structures that have never been discovered by human scientists, and everything is actually automatic. We can generate code, automatically generate code based on this data, and this code can be used to describe the family, the parameter-defined space of this negative Poisson ratio structure. Like these structures are discovered by our code from our pre-computed data sets. And also we can discover some key mechanism. For example, for this kind of structure, why is negative Poisson ratio? Because it's because of this beam deformation. And And for this, it's because of this joint rotation. And we found this kind of mechanism. There was actually some two-dimensional version came up with by human scientists, but computer doesn't know this, by the way, but it can automatically discover the three-dimensional version purely based on simulation and data-driven exploration. We also did some real tests to show our simulation actually agree with the real mechanical test. Well, that's not surprising because it's linear FEM simulation and the deformation is not that large. So we can actually predict what the structure will behave within this range of deformation. And we verify that our discovery, our computation is within the range of like 10% error between the simulation and the real design. Yeah, so basically that's my last story, I think, due to the time limit. So we want to go from computation to the mechanism discovery, to automatically explain what will happen and to automatically discover what kind of structure can lead to the best performance given some design goals. So yeah, I think I will end up my talk now, and maybe I will show you, well, I didn't go through the fluid, but I can show you some videos. So these can be some relaxing videos, like I can make it in the end. So that is my research, mostly about my research during my PhD. So we create different types of visual effects for Hollywood movies. Like we create different types of data structures for to simulate fire, smoke, water that can run on large-scale computers and can be shown in real movie effects. Like this is another data structure that can accelerate the numerical solver of Navier-Stokes equation and help us to focus on the region of interest, but without sacrificing too much of the details around it. So that's a data structure, and we can also boost the performance by like 20 times, which is very useful for the movie industry. And this is another data structure I invented. That's my PhD thesis. So it's about simulating complicated codimensional geometry driven by surface tension. So I can show you some videos that like real bubbles and the bubble blowing, breaking, and the topology changes and the shape changes are all solved on a very simple, on a very Lagrangian, very dynamic data structure. So basically my research is about creating data structure and the solvers on top of it to solve different types of physical problems, especially the structure and geometric problems. This is something called water bell. There's some phenomena discovered by some fluid mechanist John Bush at the lab at MIT, and we try to simulate these phenomena by using our new data structure. Basically, this kind of data structure can simulate infinitely geometries with infinitely thin thickness, which is infeasible on a grid. So we need some new representations of these geometries, and these geometries can actually help us to solve problems with geometric complexity that is hard for volumetric mesh structures. We also use this data structure to simulate different types of viscous fluid like paint we have seen in our daily life, and also many different other viscous phenomena like the toothpaste and the mayonnaise and the pizza cheese. And this video shows the different types of elements, like green is volumetric tetrahedron, blue is triangle, and red are segments. So all of them combined together, and we solve the Navier-Stokes equations on this structure to generate the motion of this complicated codimensional viscous flow. Yeah, so that's the end of my talk. Thank you, everybody.